Here's a few examples of converting equations from polar to Cartesian and back the other way. We did just a little bit of this in class, and let's do some more. Here's an equation. This is an equation in Cartesian coordinates, and it's not a random equation at all. The x minus 2 squared plus y minus 2 squared, that's a Pythagoras type quantity. In fact, it's a distance formula calculation. It's the square of the distance between x, y, and 2, 2. Setting that equal to 8, well, that's going to be a circle. X minus h squared plus y minus k squared equals r squared. That's a circle. And in fact, let's see if this will actually plot it for me. Should be able to plot this thing. And that's going to be a circle at center 2, 2, and radius square root of 8, or 2 root 2. Why does it not look like a circle? As usual, like with a calculator or a computer, I didn't set equal scaling yet. If I do, it'll be a circle. Okay, but right now we're not so interested so much in the graph. We're interested in sort of doing the algebra. We always want to combine them, but we're going to focus on the algebra right now. So this is a circle. We'd like to say, well, does this have a nice polar description? If I put this in polar graph paper, is it going to be nice? Is it going to have a nice polar equation? So let's, well, I guess I can keep that on the screen. Okay, so the two strategies were just plain plug in r cosine theta for x, plug in r sine theta for y, or maybe do some algebra first to see if we can get x squared plus y squared popping out, which might simplify things. Let's go ahead and do the algebra first strategy, because that's a little more sophisticated. So we're going to use a squared plus 2ab plus b squared, and we're going to get x squared minus 4x plus 4 plus y squared minus 4y plus 4 equals 8. And I set this up to be somewhat special. Notice the 4 and the 4 and the 8, those all cancel. That doesn't have to happen for this to work, but oops, I wanted this to be kind of nice. In particular, that's why this thing goes through the origin. The center's not at the origin, definitely, but it goes through the origin, because now we can see if you plug in 0 for x and 0 for y, it'll certainly be a true equation. Okay, so the reason that was useful is look what's happening. I'm getting an x squared plus y squared, and that's a nice thing to see. It's always a pattern you want to look for, or even try to engineer if you're, as long as you're not doing something illegal. That means that at least the x squared plus y squared, that's just r squared. Okay, that's one of our basic conversions. Now x alone, you can't do anything fancy with that, but we can just say that's r cosine theta. That's one of our fundamental conversions, and y is r sine theta. It's been a while since we've used those, but it was good practice. Now, I'd like to divide everything by r. Is that legal? Well, the only reason that might not be legal is if that would eliminate an r equals 0 that is legal in the equation. Well, you know what? R equals 0 is in the equation, so we're just going to have to make sure that once we do that, we can still achieve r equals 0. Okay, and to be honest, I don't know if the book even worries about this. I'm going to move everything over, just clean it up a little bit. That looks good. You can't always get it in the form r equals a function of theta, but that's the preferred form if you can. If it's really ugly or if it seems like it's not possible, then it's not a big deal. But this is the preferred form. Now let's see. Could we actually get r equals 0 there? Well, all we'd need is an angle theta where cosine theta and sine theta are equal and opposite. Yeah, we can definitely do that. Like, for example, 3 pi over 4 for theta would work. So that means that the dividing by r was fine, and it usually is, but it's a little bit of a tricky point. So that's one example. That was converting from Cartesian to polar. And again, to get a start on it, you don't even have to do this algebra at the start if you don't see something good to do. You just really plug in r cosine or sine. Then mainly it's about simplifying. Okay, here's a really simple one. R equals cosine theta. Somewhat similar, very similar to one we did in class. If you're coming from the 2011 class, that is. So the problem here is going from polar to Cartesian, you really want to look more for the pattern matching. You can't get, it's not so easy to get an easy start by putting in r cosine, r sine like here. And the trick often is the patterns we're looking for are things like r squared or r cosine or r sine. Let's just multiply both sides by r. A lot of people like to try to square both sides. That's not going to be real helpful. That would give an r squared, but it wouldn't give you what you want on this side. Multiply both sides by r is a good technique. Now r squared is x squared plus y squared. That's one of our basic rules. And r cosine theta, that's equal to x. In a sense, we're done here, but let me show you something that we really need to be able to do, and that's completing the square. This, I claim, is a circle again. So I'm going to put everything on one side, plus y squared equals 0. Now, the y squared doesn't have to be messed with it all. It's already just a square of something. But let's mess with the x squared minus x. Okay, so that is x squared minus x. Well, can I express that as something like a perfect square? Yeah, I can. I claim I can do that. If I take x minus 1/2 and then quantity squared, what is that going to be? The key is with completing the square, I think you'll remember this at least, is you just take 1/2 of this coefficient, which was a -1. That's where the -1/2 comes from. Now, what would x minus 1/2 squared be? Would that be exactly the x stuff here? Not quite, but close. X squared, that matches. Minus 2 times x times 1/2, that's going to give you minus x, that matches. But it's also going to give us a plus 1/4. Oh, that's not there. You know what? There's an easy way to fix that. Just subtract it right back off. Now, that's not exactly, it might not be exactly the sequence of steps you're used to for completing the square, but that's the way I often do it. You just take 1/2 of this, you write that down, you know that's going to be the main thing, and then you just compare and see how it's different. And the only way it's different is this has a plus 1/4 that it shouldn't have. Then just kill it right back off. And then we could move the constant over. And so what we've got is not only the algebra, we've got a geometric result as well. This is a circle with center 1/2, 0. And I'm going to write that as 1/2 quantity squared. And write that as a y minus 0. Center's 1/2, 0, and the radius is 1/2. So in a sense, we're done at this point, but I'm often going to want you to do this. I'm going to ask things like, can you recognize this Cartesian equation as a familiar shape? And you're going to have to review completing the square at that point. Okay, here's a little more complicated one, converting. We're going to try that same technique, r squared equals 4r plus r cos theta, because that at least gets 2 of the 3 parts into a nice form. It gets this into an r squared, this into r cosine theta, which is x. So let's start converting anyway. So that's x squared plus y squared equals, now don't be afraid to partially convert as long as you know you're not really at the right answer yet. This is a kind of a weird mixed bag. Okay, so, well, how can we get that r? Well, there's a couple of techniques. One is, it's not pretty, but even if you have an r standing alone, you can write it as just square root of x squared plus y squared. And that's essentially, that's an answer. It's just not a really pretty answer. A better way to do it is isolate that r. So go back a couple steps. Okay. And now square everything. It's going to get kind of ugly, or kind of, I don't know, ugly, but kind of more complicated, let's say. And that's going to be 16r squared. Now that I can convert. Whoa, that's not what I wanted. Okay, and so it's going to be all this stuff. And then that's going to be the quantity x squared plus y squared. That's kind of nice because there's no square roots in it. Okay. And it sort of shows you, okay, it's a polynomial equation in x and y. It's definitely not something that's familiar. This is a more complicated curve, definitely. And there's a lot of cool mathematics of these kinds of curves, but it at least gives us an answer. So sometimes I might ask you, get into Cartesian and make sure your answer doesn't have any square roots in it, in which case this second strategy might be good. But this one definitely should be regarded as a somewhat more advanced example.